In this video, I want to motivate the idea behind eigenvalues and eigenvectors, what they mean and why we want to look for them. But before I give you a specific definition for what is an eigenvalue and what is an eigenvector, I want to explain the types of problems that we are going to be considering. So I want you to keep this problem in the back of your mind at all times when we discuss eigenvalues and eigenvectors. First, the setup. The setup is that our matrix A is going to be a square matrix. So let's assume that A is n by n and we stay fixed with that. Eigenvalues and eigenvectors are not defined for rectangular matrices. So maybe I'll write this. Eigenvalues and eigenvectors are not defined for rectangular matrices. Where M is not n. Of course, a square is also a rectangle, one could say. So our setup is such that the matrices in our consideration will be square matrices, n by n. Now, in the first part of the course, so up until this point perhaps, the central problem that we were looking at was the problem of ax equals b. So we were looking at this problem and we said we were looking for vectors x that would satisfy this equation. These types of problems relate to balance or equilibrium or steady state. They admit, so problems that require us to find a particular balance between, say, the columns of A to reach B, or some kind of equilibrium position or steady state. These are issues that can be defined in problems that ultimately would admit an AX equal to B type of representation. Now, the problem that we're going to be looking at in eigenvalues and eigenvectors is not one of this equilibrium or balance state, but rather we will be looking at change. So eigenvalues and eigenvectors help us to look at change. So what is change? For those of you who've taken calculus, you've seen change in the form of differentials. So you could say differentials. Or difference equations. And it is absolutely true that differentials can be approximated using matrices. In fact, that's how they are calculated on your computer. They're not really, or not every function will have an elegant closed form equation when you find derivatives or differentials. But because I don't want to assume that any of you have taken calculus or are interested in taking calculus, I will give an example that we can understand on our own just using logic, and will display the point of using eigenvalues and eigenvectors and how they come into play. The key observation is to always keep in mind that the matrix A can be viewed as a transformation from, Rn to Rn. Okay, so what does that mean? It means that A takes a vector with n components, or if we take a vector with n components and multiply it by A, we will get another vector with n components because this matrix is n by n. So A can be viewed as a transformation. So the question is how this transformation might affect a particular vector sort of going forwards. For example, if you have some initial vector x0 and then you apply this transformation A, you're going to get the next vector, let's say x1 equal to A times x0. So we change the vector x0 into, or map it from x0 to x1. Then let's say we apply the change represented by A yet again. Well, we're going to get a vector x2, which is now A times x1. But if you use the fact that x1 is A times x0, you get that x2 is actually x0, or I should say A squared times x0, and so on. So we're looking at this sequence of vectors that represent some kind of state that has changed from the beginning. So initial state x0 somehow has changed into state x1, then has changed into state x2, and so on. And we see that, in fact, the n plus first state is obtained from the previous state by a transformation using A. Now, if we always have this rule, it turns out that xn plus 1 is actually a to the n applied to the vector x0. So then I ask this, if we are given, maybe I'll write it, if we are given the matrix A and the initial state x naught, how can we find the nth state, right? I think I have a mistake here. That should be an n because we start at 0. So this is n. So if we are given A and the initial state x0, how can we find, or how can we determine the nth state xn? Right? Well, you'd say, well, that's simple. Just multiply by a n times. Or compute the matrix A to the power n. But that is an awful lot of multiplication that requires a lot of computational power to just blindly multiply matrices. So that would not be a very efficient solution, and oftentimes their systems in practice are too big even for a computer to solve. So we want to look at ways to solve that more efficiently. Now, why are we interested in these types of states? So let me give you an example where this setup over here makes sense, and why we would, and how we would interpret this nth state x sub n. And could we even define something like x infinity with a to the infinity? What would that even mean? So here is an example. The example that I want to share comes from Markov matrices. I can define Markov matrices in simple terms. These are n by n matrices. The terms inside, the entries inside a Markov matrix are probabilities. So they're values between 0 and 1. And the terms in each column add up to 1. Why is that? So what kind of representation could we have by Markov matrices? Well, imagine all the people, let's focus our attention on people living in Paris and people living in London. And imagine that every year, people from Paris either stay in Paris or they move to London. And people from London either stay in London or move to Paris. So I could build a matrix that will record for me the proportion of people who have come from Paris or who have come from London in each of the cities. So for example, if 80% of the people, I should write an 8 there. Okay, maybe I'll write the matrix and then I'll explain what the numbers mean. So how could you interpret these numbers? You look at from Paris to Paris, from London to Paris. So if this year I look at the number of people who live in Paris, this column tells me how many of them were in Paris last year, for example, and how many came from London. So we see that this year's population in Paris comes from 80% from Paris, or is unchanged, and 20% comes from London. Similarly, if we look at the population in London this year, we see that 30% of it came from Paris and 70% are people who already used to live in London. Now, the assumption here is that the change in population, that migration happens according to these rules from one year to the next. Of course, this is a simplification. This is not exactly how the world works, but there are systems that can be approximated by such a simple representation. So one example could be obviously this migration. Another example could be, imagine you have cell phone operators or cell phone providers. And then what you have here is the distribution of the market. So how many of the customers of the first provider used to be customers in the previous year, and how many switched from the other provider? And then how many of the second provider's customers were loyal, and how many switched from the previous provider, right? So let's say that this change is more or less the same every year. So this is the assumption that the change is more or less the same every year. And this change will be represented by the matrix A. Now imagine that the initial state x0, which could be the number of customers when the cell phone was invented, or the number of customers this year, it doesn't matter. We choose what our steady state is. And we assume that, in this case, we're talking about population. So assume that Paris started with 1 million people and that London also started with 1 million people, okay? If we started like this and we applied repeatedly this migration procedure, I can ask the question, 100 years from now, how many people are in London and how many people are in Paris? If this year we have 1 million in Paris and 1 million in London, and every year the population migrates according to this matrix, then I want to know what will be the population of Paris 100 years from now, and what will be the population of London 100 years from now. Also, we might want to ask, will the population stop? The change in population, will it stop at some point? And to answer these questions, we have to look at eigenvalues and eigenvectors. So again, just to summarize, when we talk about eigenvalues and eigenvectors, the setup is that our matrix A is n by n. We will have some initial state, maybe I'll denote it by U0 as an initial state, because I will reserve X for eigenvectors. And let's say UN will be the nth state. And what we will discover is that using eigenvectors and eigenvalues makes the computation of this UN particularly easy. Okay, more of that in the next video.